right. So, in our course selected topics in decision modeling, we are now in lecture 18, and here we shall discuss assignment and traveling salesman problems, right. So, assignment and traveling salesman problems. In our previous lecture, we are in the middle of solving assignment problems by branch and bound algorithms. If you recall what I said at that point of time, that we really do not solve assignment problems by branch and bound algorithms. There are powerful methods, exact methods. Obviously, branch and bound is also an exact method, that is the called Hungarian method, and we shall solve mainly the traveling salesman problem. When we solve traveling salesman problem, we shall make use of assignment problems as to find a quick bound. At that time, obviously, we are not going to solve that assignment also with branch and bound, because there are quick methods called Hungarian methods. But here is a quick example how you can solve assignment problem using branch and bound. This will really make our understanding clear about the assignment problems. So, we have taken up this assignment problem in our previous class, and we have seen how we can quickly find a bound by really seeing. See, the assignment problem essentially is that there are 4 jobs and there are 4 machines, and we have to allocate these jobs to the machines in such a manner that every job is done by exactly one machine, and one machine does only one job. Is it all right? But then costs are different, like job A, if you want to do by machine 1, cost is very high, but if you do by machine 2, cost is very low. Is all right. So, obviously, machine 2 is a better option for job A, right. So, what should be the allocation that minimizes the total cost? So, that is the assignment problem. Now, in this particular problem, what we have done previously, a quick bound to the minimum possible solution can be found out by simply noting the lowest values column wise or row wise. Anyhow, we have done it column wise. So, in column wise, you see in the first column the minimum is 11, second column 8, third column 8, and fourth column 21. So, if you add them up, then you get 48. So, this is a bound to the assignment problem that we have taken. But is it an optimal solution? The answer is this is infeasible, and therefore, we cannot say this is the final solution to the assignment problem. Why? Because here look here, job D is assigned to both machine 1 and machine 4. Obviously, this is infeasible, right. As I said right in the beginning, every job should be assigned to an unique machine and vice versa. So, we have the total solution, but it is infeasible. Then what should we do? We should then branch. So, I request you to think, how do we branch this particular problem? Again, you can do row wise or column wise. Just think over how can you branch, right. So, you can see how this is possible in our next slide. What we have done, look here, the 1, that is machine 1, has to be put either to A or to B or to C or to D. There cannot be any other option, is it not? It should be one of the 4. So, those could be our branching, that is either A to 1 or B to 1 or C to 1 or D to 1. Are they mutually exclusive? Yes. Are they collectively exhaustive? Yes, because one has to be assigned either to A or to B or to C or to D. So, branching really fulfills our criteria of mutual exclusivity and collective exhaustibility. Having said that, how do I find bounds for each allocation? Let us look at A1. So, you see A21 is already done. So, when I take this A1 branch, A21 is already done. So, we have cut it off, because once A21 is done, neither A nor 1 can be allotted to anyone else. Is it all right? So, that is what we have done. We have cut off machine 1 and job A. So, now we are left with this small matrix B, C, D and 2, 3, 4. Again, if we find the bound, how do we find? See, machine 2 then can be allotted to 2, because out of these numbers 10 is the lowest, out of these numbers 8 is lowest, out of these number 21 is lowest. So, the highlighted portions would be our allotment, right. So, in fact, let us write down that allotment also. The allotment then will be A to 1, which is already known, B to 2, C to 3 and D to 4. Right. And is it an unique assignment? Yes. Is it feasible then? It is a feasible assignment solution. But what is the total cost in that case? It will be 94 plus 10 plus 8 plus 21. So, this is going to be the total cost. How much is this? 104, 112, 133. Alright. So, this is 133 and it is a feasible solution. So, look here, that is written there. That is, we have 133 feasible solution we get if we do A to 1. So, A to 1 subsystem is 133 feasible. See, the TS when we have done, that is the total system, at that time we have not taken out A or 1. So, that is the difference between the subsystem A1 and the total system. Another example is given here, that is D1 subsystem. So, what is D1 subsystem? In the D1 subsystem, we have first of all D to 1. So, obviously, D and 1 they are removed. In the remaining matrix, the allocation is A to 2, because that is the minimum, C to 3 and again A to 4. So, again look here, A is allotted to both 2 and 4. So, this solution is not feasible. So, value 11 plus 8 plus 8 plus 68. How much is that? 11 plus 8 plus 8 plus 68. How much? Please calculate. 27 plus 68, 95. But is it feasible? No, it is infeasible. So, 95 infeasible is written there. All right. Now, similarly, I am not showing the details, you can also calculate the bound for B1 and C1. They are found respectively 111 and 145. So, what is to be seen now, that look here, we have now found bounds of the solution 133, 111, 145 and 95. Now, one thing to note, see, the tree is a network. Out of this network, these are my end nodes. You see, what are some end nodes? The end nodes are those which are not further branched, right. That means, they are at the end of the the tree. So, out of all the end nodes, if you compare and then find out the lowest in case of minimization and highest in case of maximization, and then find that bound, and if we find it feasible, we found the optimal answer, right. So, which one is the lowest here? The lowest is here, right. The lowest is here, that means this is a candidate for further branching. Why? Because no point branching A1 further, because anyway we have feasible solution. So, this A1 is fathomed. B1 is also fathomed, right. A1 is fathomed. Why? Because the best solution is found. B1 is also fathomed because the feasible solution is found. C1 is infeasible, D1 is also infeasible. So, they are not fathomed, you can branch it further. Which one will you choose, C1 or D1? Obviously, D1, because that value is lower, right. So, if you branch C1, obviously we are not going to get any value better than 145, it will be worse than 145. So, since we already have 95 here, we can dig it further. Question is, look, already there is 111 which is feasible. So, anything if you get feasible out of C1 later on by branching it further, obviously we are going to get something which is worse than 145. What value is that? Because that will be always lower than higher than 111. So, that means there is no need to really go further into C1. Is it all right? So, this kind of logic you must use, that which one should be we should branch further and which one we should not, right. So, having said that, we need to now branch D1 further. So, let us see how it goes. So, look here, now we have taken out the A1 and D1, and then it could be A2, it could be B2, it could be C2. So, this is the D1 A2, that means D1 and A2, this portion D1 and A2, then D1 and B2 and D1 and C2. So, two examples are shown here. If you see D1 A2, then these two has to be cut, because D1 is cut, that means D is cut, then 1 is cut, then A2, A is cut and 2 is cut. So, when all those are cut, you have only a matrix available, that is this part, right. So, only a small portion is remaining. Now, again 8 and 76 they are lower if we do column wise, but that is an infeasible solution. The total comes 11 plus 8 plus 8 plus 76, that becomes 103, and it is an infeasible solution. So, look here, that is what is written there. If I go to B2, then we see that after cancelling out D1, which was our earlier one, and then B2, then we get this portion which is 54, 68, 8 and 76. The bounds are 8 and 68. So, what should be the value? The value should be then 11 plus 10 plus 8 plus 68. This becomes 97, and it is a feasible solution. Is it all right? So, we get a feasible solution here, and C2 when we calculate, we find it is 221 infeasible. So, how do all of this compare now? Let us look at in our next slide, then how entire thing compares. So, what are the n nodes? Let us tick those n nodes, right. Let us tick all the n nodes that we have found so far. So, A1, this is one, B1, this is an n node, C1, it is another n node, A2, B2 and C2. So, all are ticked. So, D1 and TS they are not n nodes, because they are branched further. Now, compare bounds of the n nodes. Compare the bounds. Which one is the best possible value? Which bound is the best from a minimization problem point of view? It is this one, 97. See, this is the lowest, and it is a feasible solution. So, look here, if I branch any one of them the other n nodes further, we are not going to get anything better than the value that we already have. Since this is what it is, it automatically therefore this is our best possible value, that is 97 feasible. Is it all right? So, that is how we solve, and then the optimal allocation is the highlighted one, that is A to 4, B to 2, C to 3 and D to 1 and T C is 97. I hope it is clear now, right. So, that is about solving assignment problem by branch and bound, but as I said, we are not going to solve assignment problems by branch and bound method. We shall solve by Hungarian method when we solve what is known as the travelling salesman problem. So, let us now move over and see the travelling salesman problem. The travelling salesman problem deals with finding a minimum cost, distance or time tour for a salesman visiting n cities, where each city is visited exactly once, and the tour ends with the salesman returning to the starting city. So, he starts from a city, goes to every other city exactly once, comes back to the starting city, and what should be his route, considering that he wants to move the minimum distance or minimum time or in minimum possible cost. That is what we need to find out. So, a tour is a complete route through the n cities where no city is visited more than once. But then there could be various sub tours. A sub tour is a round trip that does not pass through all the cities. So, the solution of travelling salesman problem really requires that we block all the sub tours, and this is not going to be easy, because there could be so many sub tours in a particular problem that we consider. Let us see what are they. So, here is an example, there are 5 cities, and all these 5 cities are connected by paths. You can see, you can go from 1 to 2, 1 to 3, 1 to 4, 1 to 5. Obviously, all paths may not be available all the time, is it all right? But then this is a complete thing that is shown here. Question is, how do you go from 1 to 2 to 3 to 4 to 5 and come back to 1, so that the total cost or total time or total distance is minimized, or total profit maximized also, that could be another case as well. So, look here, here is an example of a feasible tour, that is 1 to 2, we have 1 to 2, then 2 to 5, 5 to 4, 4 to 3, 3 to 1, right. So, this is a feasible tour. You can also think of obviously 1 to 2 to 3 to 4 to 5 to 1 possible. You can go from 1 to 3 to 2 to 4 to 5 to 1, or 1 to 4 to 3 to 2 to 5 to 1, 1 to 2 to 5 to 4 to 3 to 1. So, you see there could be various combinations that are possible, and such combinations are going to increase as the problem size increases. Is it all right? So, if we have, let us say, a 10 city travelling salesman problem, it could be that much more complicated. But then the problem is really not complex, because we have so many tours to compare. That itself is not such a big problem. What is the problem really is how to block those sub tours. So, supposing we have 1 to 2 to 3 and come back to 1, and so and then 4 to 5 to 4, you see they are not allowed, they are all sub tours. So, can you think of all different sub tours that you can think? right. So, you see 1 to 2 to 1, 1 to 3 to 1, 1 to 4 to 1, 1 to 5 to 1, 2 to 3 to 2, 2 to 4 to 2, 2 to 5 to 2, etc., etc. These are all size 2. What about size 3? 1 to 2 to 3 to 1, 1 to 2 to 4 to 1, 1 to 2 to 5 to 1, then 2 to 3 to 4 to 2. You see, similarly, there are subtooths of size 1, size 2, subtooths of size 3, subtooths of size 4, and all of them has to be blocked, right. That is a non-trivial task. So, let us look at then some of these what we have, right. So, before that, so all those subtooths have to be blocked, right. So, let us look at the formulation. The consider a TSP of n cities I equal to j equal to 1 to 3 to n. Cij is the distance or cost, whatever you say, from city I to city j, and Cij equal to m for I equal to j, because there is no question of going from 1 to 1 or 2 to 2, etc. So, they should be blocked, and therefore, we can put m in 1 to 1, 1 to 2, 1 to 3. M is a large positive number, anything you add to it, small numbers, or deduct from m, m remains m, right. So, therefore, as you can see, the objective function is minimize z equal to sigma I equal to 1 to n, sigma j equal to 1 to n, Cij Xij, sum over I Xij will be 1, and sum over j, not I, this should be j really. So, and sum over j, Xij will be also 1. So, therefore, that means that the salesman must arrive at each city exactly once, and salesman must leave each city exactly once. So, that gives those two conditions, and Xij could be 0 or 1. If it is 1, that means it goes from city I to city j, and 0 means it does not, and all subtooths must be blocked. So, that is the formulation, and these formulation say here is that how to block the subtooths, that has been shown. So, for the 5 TS problem, Xij plus Xji should be less than equal to 1. What does it mean? That if Xij equal to 1, then Xgi should be 0. If Xgi equal to 1, then Xij should be 0 for all I, for all j, I not equal to j. Xij plus Xjk plus Xki should be less than equal to 2, right, because if 1 to 2 is there, 2 to 3 is there, then 3 to 1 cannot be there, all right. Similarly, Xij plus Xjk plus Xkl plus Xli should be less than equal to 3. That means, if 1 2 is there, 2 3 is there, and 3 4 is there, 4 to 1 should not be there, right, only 3 of them should be available. So, all these equations, all these constraints are to be written to really make the problem formulation. So, you can see these really makes the problem NP hard. What does it mean? Complexity goes up exponentially with problem size, right. So, solving a 10 by 10 problem is like solving 10 9 by 9 problems, right. So, that sort of complexity increase really happens. So, it is not that you cannot formulate an LP for a travelling salesman problem, you can do it, but solving will be enormously difficult. So, we have to find some methods. The branch and bound method works well for some size, but beyond a certain size even branch and bound will fail. Then we have to use heuristic methods, meta heuristic methods, which we shall discuss in due course of time, right. Let us now see how branch and bound can be made use of for solving the travelling salesman problem, right. So, let us see how it is. So, this is how again we formulate. So, the total formulation is minimize z equal to sigma I, sigma j, Cij, Xij, sum over I Xij equal to 1, sum over j Xij equal to 1 and Xij equal to 0 or 1. So, does this formulation reminds us of a formulation of some other problem, right? Think over, this is nothing but the assignment problem, right. What happens in assignment problem? If you really take out the subtour blocking, then the remaining formulation is exactly same as that of the assignment problem, right. So, that means supposing there is no subtours, the assignment solution is a complete tour itself, then the assignment solution itself is travelling salesman problem. But then the assignment solution need not be, right, giving a solution which is also the TSP solution. It need not, because the assignment solution may lead to a TSP solution which is having subtours, right. So, that is where the trouble is. But anyhow, let us go ahead and see what exactly it means, right. So, that is yes, without subtour blocking, assignment problems and the TSP problems have the same formulation. Hence, solution of the corresponding assignment problem provides us with a bound for the travelling salesman problem. So, as TS problems are usually a minimization, corresponding assignment problem solution gives us a lower bound for the TS problem. Usually, the assignment problem has an easy solution methodology, that is Hungarian method, right. So, if the corresponding assignment problem solution becomes a complete tour, it is also the solution for the TS problem. So, I already said that. Let us go further. So, what is the methodology? Methodology should be therefore will be like this: step 0, ignore the subtour elimination, resulting problem is assignment. Solve the assignment problem using Hungarian method. If the optimal solution provides a complete tour, that is no subtour, then it is also TSP optimal solution. Stop. Otherwise, the assignment optimal solution yields subtours, right. Then go to step 3. Step 3, select a subtour with the smallest number of cities. It creates the smallest number of sub problems. Let k be the number of cities in the selected subtours. So, you see the solution gives a subtour. Now, there will be usually 2 or 3 subtours. So, take the smallest subtour, right. Take the smallest subtour and then branch it into k sub problems. If the subtour has got k legs, then make k sub problems, right. That is how the branching. Now, each sub problem again can be solved by assignment algorithm, is it all right, and then follow the methodology. We know that find out those bounds and see all the end nodes, and the one that gives us the best possible solution will be our solution, right. Continue the process until we get a feasible bound, that is lowest, for minimization of all the bounds of the end nodes. But if you cannot find that, then we have to fathom all the unexplored sub problems. So, this is how the TSP can be solved by branch and bound procedure. Let us take up a problem. So, here is a 4 city TSP for minimizing costs as given in the matrix below, right. Since the TSP does not involve moving from a given city to itself, so we can replace all the corners as m, is it all right. So, m is a very high value m, and anything you deduct or add small numbers, m remains m, right. So, this is how is our the matrix, the TS problem matrix, and we can solve this by assignment problem to find the bounds. So, let us solve by assignment problems. So, what exactly we do in the Hungarian method? We do the row wise and column wise reductions, right, and after those reductions we find the zeros, and then the zeros we try to allocate. That means, we make our allocations in those zeros. But if we cannot, that means, we do not succeed in making all the allocations, then we have to create more zeros, right. Let us see how it goes. So, this is our original matrix. So, these are the row wise smallest numbers 4, 5, 5 and 4. So, what I do? I deduct those numbers from every number and then I get the resulting matrix. So, M 0, 2, 3, say I have deducted 4. So, M 0, 2, 3. So, by similar method 1 M 2 0, 2 0 M 1, 1 0 2 M. So, M minus 4 becomes M, because anyhow it still remains a very large number. That means, A to A should be blocked really. So, that is the row wise reduction. Then we do the column wise reduction. So, again we see these are the smallest number column wise. Now, if we do those reductions, then this is our resulting matrix, that is M 0 1 0, 0 M 0 0, 0 0 M 0, 3 0 1 M, right. What we have to do now? We have to now carry out assignments. How to carry assignments? Assign in the unique zeros. So, look, this is an unique 0. So, some assignment can be done here, but then this 0 gone, right. So, this 0 is gone also. Moment these two zeros are gone, then this becomes an unique 0. So, we make some assignment, that means these two zeros are gone. So, now this becomes unique and this becomes unique. So, look here, this is how we make the assignments, right. So, that is shown in our next slide, that is So, this is our next slide. So, all those assignment have been made, and that is A to C, B to D, C to B and D to A. So, and then the total value comes out to be 21. Is it all right? So, this is the assignment solution. So, what is the TS solution? We see A to C, C to B, B to D and D to A. So, TS problem solution will be obtained from the assignment solution, and that should be A to C to B to D, to A, right, that A is missing. So, A to C to B to D to D to A, and it is also feasible because we get a complete tour, right. So, hence it is the optimal TS problem solution also, and what is the TC? That is 21. So, we are lucky here that we solved the assignment problem and we find the assignment solution is also the TS problem solution. So, we get the optimal solution for the TS problem, right. So, this is a simple problem, really there is no need to really go for branch and bound. The optimal solution for the assignment problem becomes the optimal solution for the TS problem, and there is no need to branch or further bounds to be found. Is all right. The bound for the total problem, the TS, the total solution is 21, right. So, and that itself is feasible. So, that is the TS problem solution. But we may not be lucky like these all the time, right. We shall take more complicated problems in our next lecture, right. So, thank you very much.